The next example, we're going to expand on permutations a little bit, because if you think about our last example, number 2, we had 8 bands and we gave 8 different places, and that's just typically not how it works. Typically, if we have 8 bands, we may only award 3 places, maybe 4 places, but typically all the bands won't get a place finish. So that's what this example is about. It says, suppose in example 2, you want to know how many different ways the first, second, and third place rankings in the competition can be awarded. So we're going to stop at first, second, and third, and no other awards are going to be made. Then how many different awards and how many different arrangements could there be of 8 different bands shooting for the 3 different places? So what they've outlined here is a good strategy. How many ways can you select a band for first place? And there are 8 different bands. And how many bands then are left to get second place? And there's 7. How many bands are to get third place? And that's 6. That's all that we're concerned about. So we take 8 times 7 times 6. Our fundamental counting principle is 336 permutations, because that's the way we wanted those 3 events to happen, first, second, and third. And we can calculate this a different way, and this is where they bring in our factorial notation that we talked about a little bit. And they give us another way of calculating these results. What we can do is we can use our factorial notation to help us generalize our results. The number of permutations can be found by using factorials by finding the number of permutations of all 8 bands. So if we gave 8 places to 8 bands, we'd say it's 8 factorial, n objects taken n at a time. But we don't want to give all 8 places, we only want to give 3 places. So that means there are 5 bands that are not given a place finish. So we want to get rid of these 5 place finishes that we would have calculated in our original if all 8 bands got a place. We want to get rid of the 5 places that they didn't give away. And those 5 places are then in factorial notation. 5 factorial means 5, 4, 3, 2, 1. And if we go 8 factorial, it goes 8, 7, 6, 5, 4, 3, 2, 1. And you can see what they highlighted in red. These are equivalencies of 1, which means they reduce out of your calculation. All you're left is 8 times 7 times 6. So what we do is we look at this and we say, this is a permutation of n objects taken r at a time. A permutation means we want to know how many arrangements of distinct objects, and the order in which they come in makes a difference in the order in which we place them. Well, if you're given awards, people recognize the difference between first and second place and third place. People get kind of up in arms if you give them the wrong place value. So the order in which they finish is important, and they're distinct objects. Well, in this case, we have 8 distinct objects, of which we're going to recognize 3 of them. And this is how we write our permutation of 8 things, chosen 3 at a time, or taken at r at a time. So there's our permutation notation, the way that we can write this, the n subscript p, then subscript r. It's n objects. N is the total number of objects that you have in your group, and your n minus r, r stands for how many you're going to actually select. So in our case, to look at this, we had 8 bands. We're only going to take from the 8, we're going to give 3 places, so n choose r, which is 8 choose r, get rid of the n, so we have 8 factorial all over 5 factorial, which then again can be written like this. So basically you're going to, and I think the important part here that you see is that you're going to divide out the number of arrangements of the bands that finish with the rankings other than first, second, third. So we're going to get rid of those that we counted because we're not going to give those away. So let's see if we can apply this to a couple of different scenarios. The first one is, how many different ways can 2 students be assigned to 5 tutors if only 1 student is assigned to each tutor? Okay, so you've got to think about, is this a permutation? Do we have distinct objects? We have 5 tutors and we got 2 students, and if we arrange the tutors and the students around to different ones, we have different outcomes. So it definitely makes a difference the order that we put them in, and they are definitely distinct. So we have a permutation where we have 5 distinct objects. We have 5 tutors to spread among 2 students. So it's a permutation of the 5 tutors, we got to assign them 2 students. So we would have 5 factorial all over a 5 minus 2 factorial, which is a 5 factorial all over 5 minus 2 is 3 factorial. And now remember what factorials mean. If you have a factorial, it means you have 5 times 4 times 3 times 2 times 1. 3 factorial says you have 3 times 2 times 1. Or, in the end, Your 3's will reduce, your 2's will reduce, your 1's will reduce. There are 20 ways. Now, the other way that you could think of this, and this is the way that I approached it the first time, is to show you the factorial notation and the permutation concept is there are 5 tutors. Here's student number 1, so if I go student number 1, how many ways can I assign them a tutor? There's 5. Once I assign someone a tutor, when I get to my second student, there's only 4 tutors left, and that's 5 times 4, or 20 arrangements of tutors to students. We got a few more examples here to look at permutations. An Iowa license plate consists of 3 letters followed by 3 numbers. If the repetition of the letters and numbers is not permitted, so we're not going to have repetition, how many license plates can be produced? So I'm going to write a representation of a license plate. This imagery, this picture, and how I write this helps me out a lot. I'm going to have 3 here, and we're going to have 3 other things here, because as it reads, the Iowa license plate consists of 3 letters, so these first 3 are letters, where the last 3 are numbers. So we got to figure out how many different arrangements are allowed. So let's start looking at our different arrangements. We talk about letters. How many letters are there in the alphabet? If we look in this location, how many letters could I put in this first location? Well, there are 26 letters in the alphabet, so I can put one of 26 letters in that first spot. Once I use a letter, since the repetition is not allowed, I'm down to 25. And after I use that letter, then I'm down to 24. Now I'm going to go to the numbers. In the numbers, there are 10 digits, 0 through 9, so I'd have a choice of any one of 10 there. Once I choose a digit, it can't be used again, so then we'd be down to 9, and down to 8. So the fundamental counting principle says, this is how many ways event number 1 happens, this is how many ways event number 2 happens, so how many ways are there altogether? You take the number of ways event 1 can happen times the number of ways event 2 can happen. So what we're going to end up doing is taking the product of all of these. So it's going to be a 25 times 20, 26 times 25 times 24 times 10 times 9 times 8, and that'll be our final number. So we'll come up with our calculator and we'll do the calculation. We have 26 times a 25 times a 24. Okay, we can take that answer and multiply it times our other answer. Since multiplication is commutative, it doesn't matter. So we can take it times 10 times 9 times 8. There should be a big number here. It is a total of 1, 1, 2, 3, 2, 0, 0, 0. So putting those in, whoops, wrong place. It's a bugger, missed it. Try one more time. 1, 1, 2, 3, 2, 0, 0, 0. 1, 2, 3, 1, 2, 3. We have a total of about 11,232,000 license plates that we could produce if we use this scenario. Now I want to come back and try this a different way. We can do this in permutation. In a permutation, we have 26 letters, and we're going to choose only 3 of them at a time. That's how many ways we can get event 1 to happen, which means we got 3 letters. We also have to have a second event happen. We have to have 3 numbers. So this is another permutation. We've got 10 numbers, of which we have to select 3. So we got 10 taken 3 at a time and 26 taken 3 at a time. We want to multiply those probabilities together. Okay, I want to come back and show you a feature on your calculator. Once again, there's another feature on here that we can use to make the calculations quicker. This is why the permutations are nice. We go back and we hit our math key under probability, you'll see something that has that same notation. It's NPR. So what we have to do is you have to put in our home screen, the N, come back to this screen, hit our permutation command, and then the R. We're going to do that twice. So we're going to second quit. We're going to do 26 objects. We're going to take them 3 at a time. That's a permutation, probability. We're going to take permutation. We're going to choose 3 of those. Now that'll be the number of ways we can get 26 or 3 letters out of or 26 letters of the alphabet. But I want to take that result times. Now we want the chances of event number 2 happening, which was a 10 permutation taken 3 at a time. Then we come up with the same figure. It's just a couple of different ways of getting the same information. One uses a little bit more technology and a little bit more of your capacity of your calculator than the other. Now let's go explore the second part of this question. It said, what if repetition is possible? Does that increase our number of license plates? Well, if we get to use them over again, it should increase our total number. So let's take a look. How many different ways can we choose our first number? Well, we got our letter, 26. If we can use them again, then this is a 26. And if we can use them again, this could be a 26. The same principle is in effect for our numbers. You can go 10, 10, 10. So in this case, it's not a permutation because we don't have distinct objects. Some of these objects are the same. If I go 26, 26, 26, these objects, these could all be A, which boots it out. It can't be a permutation anymore because they're not distinct. But we still can count how many. So we can do a 26 raised to the third power. I'm going to use powers because it's 26 times 26 times 10 raised to the third power. We get our total number of ways. And now if we allow for repetition, we get 17,576,000 different license plates that could be constructed or made. So I think I'm going to kind of just bypass that last example and giving you plenty of an ample opportunity to come up with some ideas on how to do permutations.